Hi, let's check few more example. The next example which is given in your textbook is carbon suboxide. Carbon suboxide. C3O4. C3O4. What about the normal idea? X into 3 plus minus 2 into 4, which is equal to 0. So 3x minus 4 equal to 0, where the oxidation state is plus 4 by 3. Plus 4 by 3. That means oxidation state of an element is a fraction plus 1.33, right? We know that it will never happen. What does it mean? Say an element which drops plus 1.33 electron. So there is no concept like that, okay? So positive oxidation state means it lost some kind of electron, right? So plus 1.33, it means plus 1.33. So there is nothing, or nobody can drop electron like that, in that fashion. Electron will be gained or dropped or lost in the form of integral multiple, right, of electron charge. Here it is plus 1.33 means a fraction of charge is dropped. Okay, it is not possible. But this oxidation state is said to be average oxidation state or paradox oxidation state. Average or oxidation state or paradox oxidation state. So paradox oxidation state or average oxidation state means oxidation state of an element. Oxidation state of an element become fraction. Become fraction. Okay. So actually oxidation state of the carbon is actually, I think, plus 2, 0, plus 2. Actually, the oxidation state of carbons are here in the carbon suboxide is plus 2, 0, plus 2. Which means 3 carbon have plus 4 oxidation state, plus 2, 0, plus 2, which is equal to plus 4. 3 carbon have plus 4 oxidation state. So in an average sense, it is each one carbon have plus 4 by 3. But actually, plus 2, 0, 0, plus 2, 0, 2 is the concept. It is not equally distributed like this. Okay. So this is the actual oxidation state, and this is said to be the fractional oxidation state or paradox oxidation state. So this is also valid. This is valid. You can choose paradox oxidation state from your answer key. Okay. If there is no actual oxidation state in your answer key, then you can choose paradox oxidation state. Okay. But pseudo oxidation state is never accepted. You know what is pseudo oxidation state? We just discussed it before. Okay. It is never accepted. So you can accept a paradox oxidation state if there is no actual oxidation state. Okay. And let's check how this become plus 2, 0, 0. For that, you have to know the structure of carbon suboxide. Carbon suboxide having a structure where 3 carbons are connected in double bond. And each terminal we have a double bonded oxide. This is the structure of carbon suboxide. What about the electronegativity to here? So this carbon have minus 2. What about the right side? No problem, because these two are carbon. So there is no electronegativity pull. Okay, so based on this carbon, they're only surrounded by a minus 2 charge. So this carbon should offer a plus 2. What about this carbon? To the left carbon, to the right also carbon. So there is no pulling of electron. So this can offer 0. What about here? There is a pulling of electron right towards right, because oxygen is more electronegative. So this become minus 2. So this carbon should offer plus 2. So that's why the oxidation state plus 2, 0, plus 2. Okay. Okay. So In this case, you have to, first of all, you have to by heart the actual oxidation state, plus 2, 0, 0, plus 2, 0, plus 2. Okay. I think this may be, you will obtain this from the question or from the molecule C3O2. You know how to find this. Okay. So no need of by hearting this one, and you simply know that paradox oxidation state is also acceptable. Okay. The first preference is for your actual oxidation state. If actual oxidation state is not given in your choice, in your answer key, then you choose paradox oxidation state, which means the fractional oxidation state. Okay. So moving to the second example in your textbook. Tribromo octoxide. Tribromo octoxide having a formula Br3O8. 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 What about the normal sense? X into 3 plus minus 2 into 8, which is equal to 0. So x is equal to plus 16 by 3. So we know that plus 16 by 3 is a paradox oxidation state. So no problem, this is acceptable. But before that, you have to know the actual oxidation state. The actual oxidation state of bromines are plus 6, plus 4, plus 6. Plus 6, plus 4, plus 6. Okay. Plus 6, plus 4, plus 6. Ready? Fine. Listen. Plus 6, plus 4, plus 6. How you obtain that? For that, you have to know the structure of tribromo octoxide. So there is 3 bromine like this. And each terminal bromine have 3 oxo group. Oxo group means double bond out. Each terminal bromine have 3 oxo group. And the middle one have 2 oxo group like this. This is the structure of tribromo octoxide. Okay. So consider this. A pull of electron towards oxygen, towards oxygen, towards oxygen. There is 2 bonds. So this is minus 2, minus 2, minus 2. I think you know that concept. And what about here? There is no. For this bromine, from the right, it is bromine itself. So no polarization. So around bromine, minus 2, minus 2, minus 2. So this is of X. Surrounded charge is minus 6. So bromine should offer plus 6. What about this bromine? A pull of electron towards down, towards up. So minus 2, minus 2. Towards right, there is no problem. Left also there is no problem. So surrounded charge is minus 4. So it have to offer plus 4. Like that, a pull to here, a pull to here, pull to here, minus 2, minus 2, minus 2. And there is no pulling from the left bromine. So surrounded by minus 6. So this have to offer plus 6. Okay. So that's why the oxidation state plus 6, plus 4, plus 6. So the first preference is for this one. Okay. The actual oxidation state, or if it is not given in your choice, you can choose the paradox oxidation state plus 16 by 3. Okay. Ready. Moving to the next category. Moving to the next category. That is listen. That is sodium thiosulfate. Sodium thiosulfate is Na2S2O3. This is one of the typical one. It's not paradox, but there is an exception. What about the usual sense? Plus 1 into 2 from sodium, X into 2 from sulfur, minus 2 into 3 from oxygen, it is equal to 0. Plus 2 plus 2x minus 6 is equal to 0. So 2x is equal to plus 4, x is equal to plus 2. Okay. So we realize that the 2 sulfur, which is in +2. So oxidation state is +2 +2. Okay, we think that it is +2 +2. Okay, or in an average sense, it will be +2 +2. But there is some problem. It is not actually +2 +2. The actual oxidation state, to understand the actual oxidation state, you have to know the structure. The structure is S double bond O, S double bond O, single bond S. Here is ONA, here also ONA. Okay, ready. So what about the case? Consider the sulfur, a pull of electron towards here, so -2. This is a single bond towards the oxygen, -1. This is also a single bond towards oxygen, -1. What about here? No, because it is sulfur itself. So -1, -2, -1. So surrounded by -4 charge. So this sulfur have to offer +4. What about this sulfur? It is only surrounded by a sulfur. Okay, so there is no charge. So the actual oxidation states are +4, 0. +4, 0. Okay, oh, it's not +2 +2. It is actually +4, 0. So this is the most preferable one. If it is not given in your choice, then you can choose this one. Okay. And moving to the next species, which is similar to this one, sodium tetrathionate. Sodium tetrathionate. Na2S4O6. Na2S4O6. Listen. Na2S4O6. Okay. Listen carefully. What about the normal sense? +1 into 2 plus x into 4 plus -2 into 6, which is equal to 0. So 2 plus 4x minus 12 equal to 0. So 4x is equal to +10. So x is equal to +10 by 4, which means +2.5. This is a paradox one. So this is accepted. But the actual oxidation state of that 4 sulfurs are +5, 0, 0, +5. This is the actual oxidation state. This is accepted, but this is the actual one. This is paradox. Okay. And let's write the structure. S double bond O, ONA. A sulfur, double bond O, ONA. Listen. A pull of electron towards here. Since 2 bond -2, 2 bond -2, 1 bond -1. And there is no from that sulfur. So surrounded by -2, -1, -2. -5 is the surrounding charge. So sulfur have to balance it by +5. What about here? The very same front. -2, -1, -2. From here, no. Surrounded by -5, so offer +5. What about this sulfur? Surrounded by sulfur. Both sides sulfur. Also both sides sulfur, so 0. So it is +5, 0, 0, +5. This is the actual case. Okay. In sodium tetrathionate. So this is the most accepted one. If it is not given in choice, you can choose +2.5. Okay. And let's do some more cases. And the case is known as mixed oxide. What it is? Mixed oxide. Mixed oxide. Mixed oxide. Okay. Mixed oxide, or the first example is Fe3O4. Second one is Mn3O4. Third one is cobalt CO3O4. And another type of mixed oxide, that is Pb3O4. Pb3O4. So generally the mixed oxide having a formula M3O4. Okay, so the oxidation state of M will be plus 8 by 3. Check it. Plus 8 by 3. But this is paradox. This is accepted. All these four have plus 8 by 3 oxidation. This is paradox, accepted. But the actual idea or actual oxidation state means in Fe3O4, Mn3O4, CO3O4, they all exist like this. FeO dot Fe2O3. So it is a mixing of two simple oxides, FeO and Fe2O3. In the case of Mn3O4, MnO, Mn2O3. CO3O4, COO, CO3O4. CO2O4, O3. So what about the oxidation state here? Plus 2. Here we have 2 iron. So both in plus 3. So the actual oxidation state of this whole category is plus 2, plus 3, plus 3. This whole category. So total is plus 8. But it is not equally divided like this. So this is accepted, but this is more accepted. And this is a mixing of two simple oxide to form the mixed oxide. But in the case of lead oxide, it is entirely different. The mixing is PbO, PbO, PbO2. This is a type of mix, which means the lead plus 2, plus 2, plus 4. Okay, ready? This is oxidation state of lead in Pb3O4. Okay, is it okay? So this is another kind of exception, what we called as mixed oxide. So in the case of Mn3O4, Fe3O4 and CO3O4, the mixing is like this. MO, MO2O3. Sorry, MO, M2O3. In the case of Pb3O4, it is MO, 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 M2, MO2. So study it, okay? The next category, that is I3 minus. I3 minus. So oxidation state of iodine, we know that it is minus 1 by 3, right? Minus 1 by 3. Okay. But it is not minus 1 by 3. It is not minus 1 by 3. Each iodine is in minus 1 by 3. It means that each iodine is in minus 1 by 3. But it like this. Listen. Actually, the bonding is I. Iodine, iodine, iodine. Ready? And what about the 7 valence electron of iodine? 1, 2, 3, 4, 5, 6, 7. What about the 7 valence electron of this iodine? 1 here, 2, 3, 4, 5, 6, 7. What about the 7 valence electron of this iodine? 1, 2, 3, 4, 5, 6. Oh, 1, 2, 3, 4, 5, 6, 7. So it is clear that one more electron is excess. This electron is excess here. And that excess electron represents the negative charge. So the minus 1 charge is from that excess electron. So actually the charge of each iodine is not minus 1 by 3. It is 0, and the middle to one have a minus 1 charge because it gained that electron. Then the final one is also 0. Okay. So keep it on mind. Ready? Okay.
Let's check one more example. You know the composition of bleaching powder. Bleaching powder. Okay. Let's check what is the case in bleaching powder. Bleaching powder. So this is the case in I3 minus. Bleaching powder. Bleaching powder is CaOCl2. CaOCl2. Okay. So in a normal sense, oxidation state of calcium is +2, oxygen is -2. So Cl2 will be 0. Calcium is +2, oxygen is -2. So Cl2 will be 0. But it is actually calcium hypochloride. The structure is like this. CaOCl, CaCl. CaOCl, CaCl. So electron density towards here. So this is -1, this is -1, so this will be +2. And so this is clear that this chlorine have -1. And OCl whole minus. OCl whole minus means O have -2 and Cl have +1. So Cl is in +1 oxidation state. So the oxidation state of chlorines are +1, -1. +1, -1. Okay. One more. Let's check. Brown ring. Brown ring. Fe, you know the brown ring test for nitrate. This is the brown ring complex structure. FeH2O 5 times NO2 plus. And the oxidation state of iron is +1 because H2 have 0 oxidation state, but NO is nitrosonium ion. This is having a +1 oxidation state. So here we have +1 and the final will be, the answer will be +2. So this iron should offer +1. So oxidation state of iron in iron in brown ring complex is +1. Okay. So simply up to this much exceptional or special case you have to know. Okay. Moving to the next. The case is known as the simple idea. Some more simple ideas are there. The idea is known as Stock notation. The idea is known as Stock notation. So exceptional oxidation state is over. Moving to the next category, that is Stock notation. Stock notation. It is nothing but it is representation of oxidation state of elements using Roman numerals within parenthesis or bracket. Within parenthesis, which means bracket. For example, if we have potassium permanganate, KMnO4, and the Stock notation, we know that the oxidation state of manganese is +1. Manganese is +1. So the Stock notation is, listen, KMnO4, this is +7. And we have a dichromate, K2Cr2O7. K2Cr2 6O4. We have N2O5. N2O5. We have HAUCl4. HAU thrice You know how to find the oxidation state. So for finding oxidation state, gold will be 3. So like that, this representation is said to be stock notation. Stock notation. It's very easy. Okay. The next, nomenclature using oxidation state. Nomenclature using oxidation state. So nomenclature with the oxidation state is the next category. Ready? So listen, 940. Listen. Nomenclature using oxidation state. The first one is for cation. Cation. In the case of cation, if we have a cation and the cation have common oxidation states, we have cation and the cation have two common oxidation states. And the lower one ends with a suffix of "-as" and higher one ends with a suffix of "-ik". So common oxidation state of cation, the lower OS end with the "-as" suffix, higher OS end with the "-ik" suffix. Lower OS with the "-as", higher OS with the "-ik". Ready? I'll give you some examples. First one. Okay. Mario. Hello. Listen. Iron have two oxidation state, two common oxidation state. Fe2 plus and Fe2 plus and Fe3 plus. The two common oxidation states are Fe3 plus and Fe2 plus and Fe3 plus. So which one is the lower oxidation state? Fe2 plus or Fe3 plus? Fe2 plus is the lower oxidation state. So Fe2 plus should end with the "-s", whereas Fe3 plus with the "-s". Fe3 plus with the "-ik" and Fe2 plus with the "-s", right? So we know that the iron in Latin is said to be ferrum. So Fe2 plus having an oxidation state. Sorry, Fe2 plus is the lower one, and the Latin name of iron is ferrum. So it is said to be ferrous. What it is? Ferrous. Ferrous oxidation state. Ferrous is the IUPAC name of Fe2 plus. What about Fe3 plus? Fe3 plus is the relatively higher one. So this is ferric. Ferric. Okay. So Fe2 plus is ferric and Fe2 plus is ferrous. So 3 plus ferric, 2 plus ferric, ferrous. So this is ferrous and this is ferric. The lower one "-as", higher one "-ik". Okay. The next example, we have copper, and the Latin name of copper is cuprum. Cuprum. So copper have two common oxidation state, +1 and +2. Okay, so the lower one should end with the "-s". So it is cuprous. And the higher one with the "-ik", it is cupric. Ready? Next. Tin. Tin have two common oxidation state, SN2 plus and SN4 plus. Okay, the Latin name of tin is stannum. What it is? Stannum. So the lower +2 is said to be stannous. Higher plus 1 is known as stannic. The next, we have mercury, Hg. The Latin name of mercury is hydragyrum. And mercury can show a common oxidation state like +1 and +2. So the lower +1 are represented by hydra, it's not by hydragyrus, it is mercurus. So there is no need of considering a Latin name also. It may be anything. Okay. So mercury by mercurus, +1 is by mercurus, and the +2 is by mercuric.